This lecture in this video is on quality, but before we start to talk about what quality is, um, I just want to quickly review where we're at this point in frequency response. Remember that we've been talking about a series bandpass filter. We will get to the parallel case in a few more videos. And in this parallel bandpass filter, V out is across the resistor, and V in can vary its frequency from 0, which is DC, up to, in theory, up to infinity. And we derive this frequency response equation by just doing voltage divider for the voltage across the resistor, and then we took the magnitude of that, and we saw that for various omegas, if you plotted the magnitude of the frequency response, which is just the ratio of V out to VI, that you get this bell-shaped kind of curve that in general is not symmetric. It's actually steeper slope on the left side of resonance, the lower frequency side of resonance, and a broader slope on the high side of resonance. We'll talk about a special case where, for all practical purposes, this curve becomes symmetric, but it never becomes perfectly symmetrical. And for this particular bandpass filter, the maximum is when this ratio is 1, meaning at the resonant frequency we get the max where V out equals VI. And remember, the resonant frequency is a singular frequency where we have this equality between the reactance of the inductor and the reactance of the capacitor. And when these reactances are equal, they effectively cancel out, and we're left with just the resistance as the impedance of the circuit. And that's because reactants of the storage elements are 180 degrees apart, so that's why they cancel out when they're in series, because we add them up, and since they're 180 out, they cancel. So this is our resonant frequency equation that just comes from this equality. And then we also talked about a measure of frequency response called bandwidth, which is the difference of these two half power or cutoff frequencies. The cutoff frequencies comes from that these frequencies determine which frequencies get passed from the input to the output of the filter and which get blocked. So all the frequencies within the bandwidth get passed, all the frequencies outside the bandwidth are blocked or they're not passed. And then the difference of those two frequencies is called the bandwidth. Okay, so that was just a quick little couple-minute review of where we're at. Now, where we're going to start with quality is I have a handout here that shows the definition of quality. Oh, one other review item, okay, just real quickly, is that, we talked about this derivation here that shows omega 1, which is the lower cutoff or the lower half power frequency in terms of circuit quantities R, L, and C, and then also omega 2. Okay, so I just want to throw that in there real quick, that also that's part of the review. But now on to new material, and that's what quality is. So quality here, we use the symbol Q, and you can see here's the exact definition, 2 pi times the ratio of max energy stored divided by energy dissipated per cycle. But the way I like to think of quality is that it's an energy efficiency rating either for an inductor or for a filter. And it's really, basically it's energy stored divided by energy dissipated. So that's why, one way you can think of it is as an energy efficiency rating, because, if we had an ideal inductor, well, the quality would be infinity since all the energy would be stored and none of it would be dissipated, because an ideal inductor would have zero resistance, that the wire that makes up the inductor would be perfect with no resistance, so this denominator here in this ratio would be 0. But in actuality, of course, the wire that makes up the inductor has some resistance, so you're going to have some finite amount of energy dissipated. So you would like your Q of your inductor to be as high as possible, and well-designed inductors will have qualities in the several hundred range. So anyway, if you look through the handout here, you can see at the very bottom is the important result that quality is equal to omega L, which is reactance of the inductor divided by R. So if we have a non-ideal inductor, and I mentioned this in a previous video, okay, non-ideal inductor L, we often represent that non-ideal inductor with a resistance in series with its inductance, okay, where this resistance is the resistance of the wire that makes up the inductor. Remember, an inductor is just some wire that's wound up. So you see the quality of an inductor is just equal to omega L divided by the resistance of the wire that makes up the inductor. So this is just XL divided by RL. Okay, again, L here standing for inductor, not load. And as I mentioned, an ideal inductor would have infinite quality since RL would be 0, since no energy would be dissipated by an ideal inductor. But actual inductors, you want this number to be large, okay, because you prefer to have as much energy stored with as little energy dissipated as possible. So that's quality of an inductor, but you also have quality of a filter. And the quality of a filter, such as our bandpass filter, our series bandpass filter. Okay, so this just stands for series bandpass filter. Well, it's still reactance divided by resistance. However, there's a few differences. And those differences are that, first of all, the reactance, okay, omega L, it's always at the resonant frequency when you're talking about quality of a filter. Quality of an inductor, this omega could be any omega. It's the omega that the manufacturer that designed or fabricated the inductor designed it for. Now, often this omega that the inductor is designed for is the resonant frequency of a circuit if it's in a filter circuit, but it doesn't have to be. Okay, it's whatever omega the designer wants to design for. But quality of a filter, it's always at the resonant frequency. And then this R, it's not R of the inductor, but R of the circuit. Okay, so for a series bandpass filter, this is just going to be the REQ of the bandpass filter, okay, of the series bandpass filter. And we're going to see examples that involve both these quantities later on. Okay, so that's what quality is. Now, quality of a filter comes in handy, especially how it relates to bandwidth. So if, let's see, we look at, I believe it's this handout here. Let's see, nope, not that one. Okay, if we look here, what I have on this handout, and by the way, all these handouts are available on Polylearn, so you can look at them more closely at your convenience. But what this shows is taking our expression for omega 1, which is the lower cutoff frequency, that's in terms of the circuit quantities R, L, and C, and showing it in a different form that has Q and also resonant frequency. And I show the steps here for omega 1, and then you can do a similar thing and get the same form of equation with just a few differences. In fact, just this plus sign here for omega 2. Okay, now with some further manipulation here, and for typical Q values, where this radical becomes approximately equal to 1, you can show this important relationship here between bandwidth and quality, that there's this inverse relationship between the two. So a bandpass filter that has a high Q, okay, a high quality, is going to have a very narrow bandwidth. It's going to be what we call selective. Its frequency response is going to be selective because only a narrow range of frequencies is passed from the input to the output of the filter. Conversely, if Q is a low number, okay, a low Q circuit, well then your bandwidth is going to be large, or what we call broad, because there'll be a wide range of frequencies that will be passed from the input to the output of the filter. Okay, so knowing this relationship between bandwidth and quality of a filter circuit, you can, or you should be able to have a mental image of the frequency response of a filter just by hearing a number. So, if you have a low Q circuit, okay, compared to a high Q, say you have a Q of 5, that would be considered low, and a high Q circuit of 50, something like that, or higher. Well, this low Q circuit, you're going to have a broad range of frequencies. You're going to have a large number of frequencies between your cutoff frequencies, omega 1 and omega 2, that are part of your bandwidth, that are the frequencies that get passed. Okay, but a high Q circuit, well, it's very selective. It's going to have a very narrow frequency response curve. So, your bandwidth between omega 1 and omega 2 is going to be a small range of frequencies. So that's really the advantage of knowing the relationship between bandwidth and quality of a filter, is just that by hearing a number, a mental image should be able to pop up into your head of these frequency responses. Now, one last thing about quality, and that's, and I mentioned this earlier in this video, that there's a special case where, for all practical purposes, okay, so I'm going to make a little insert here. Okay, there's a special case where, for all practical purposes, okay, so FAP, for all practical purposes, our frequency response curve, okay, so frequency response curve becomes symmetric. And that special case is when the Q of the filter, so if we had a Q of a series bandpass filter that was at least 10 or greater, well then you can say that that bell-shaped curve, that frequency response curve, is symmetric, okay, meaning that the distance between the resonant frequency in the higher cutoff and the resonant frequency in the lower cutoff are essentially the same. Now, also, as I mentioned earlier, again, for all practical purposes is a key phrase here, because the frequency response never becomes perfectly symmetrical, but as long as the Q is 10, or greater than that, it's so close that for most applications, you're not going to worry about the slight difference, the slight symmetry, asymmetry that it has. Okay, well, I think that brings us up to the point now where we can do some specific problems involving a series bandpass filter. So that will be in the next video.